Hello, ladies and gentlemen. I am Dr. Claudia Albers, Planet X researcher and professional physicist. And today I'd like to bring to you another one of my articles. This one is entitled Planet X System Orbits. Now, as I pointed out in article 372 entitled The Sun is No Longer Shining, Satellite Images, the SDO eclipse season, which is not an eclipse, but it is the sun actually going dark, must be due to an object, a stellar core, or a member of the Planet X system of dead or energy depleted objects closely approaching the sun. The SDO eclipse season occurs twice per year and lasts about 24 days. Staying darker for longer and longer periods for the first 12 days and up to 69 minutes per day, and then reversing for the next 12 days. This means that the stellar core responsible for the sun going dark at these times must orbit the sun and come to it about once every 180 days. It then goes into a smaller orbit around the sun for 24 days, after which time it returns to a larger orbit. Both orbits must be highly elliptical. When in a longer orbit, the object must come into the sun's corona once about every 180 days, indicating that it must have an extremely small perihelion position. During the shorter orbit, the object must come into the sun's corona once every 24 hours. Now, these are the images that I show over and over again, explaining why the SDO eclipse season is not caused by an eclipse. And we start by comparing the Earth's curvature with the sun's curvature. This is what's illustrated here on the right hand side. And that means that the Earth's curvature is almost that of a straight line. So we can approximate the Earth, which would be covering this part of the sun in order to produce this image here, where part of the sun is dark, with this triangle. So if the Earth is covering this part of the sun, these two images are 4 minutes apart, then we would see the corona here. Well, we wouldn't see the corona below the line, which is the hypotenuse of the triangle, and we'd see it above the line. But if you compare what we see here, that's not what we see. The corona is not there. The corona here that we see here is missing there. And it's not being, well, the Earth cannot cover the corona over there, so that cannot be the Earth covering it. But what it shows, and the corona is perfectly edged, you can see the darker purple color there. So it's not being covered at all. This is where the corona ends. And this happens on both sides and indicates that the corona shrinks as darkness progresses across the face of the sun. And since the Earth could not produce that effect, it cannot be an eclipse. This is the sun going dark, and as it goes dark, as darkness progresses across the face of the sun, of course, the edge of the corona shrinks back. That's what you expect if the sun goes dark. Another thing that shows us that the sun's going dark is the curvature of the interface between darkness and light. As you can see, it's far more curved than the curvature of the Earth. There's no way the Earth is not curved enough to produce that curvature. And then we also always see completed structures at the edge. We see completed cellular-like structures, perfectly edged, in the region that is already dark, not covered by the Earth. None are partially covered by the Earth. As you can see here, the Earth was covering the sun. We would see structures at the edge that are partially covered. They don't look complete, but yet everything that we see here are complete. Furthermore, this coronal hole here seems to grow without the Earth being able to cover it. These are only 4 minutes apart. So the fact that this coronal hole seems to grow suggests, in addition, that indeed the sun is losing light emission. That's causing the darkness to progress further into regions where it was already weaker. So there were more coronal holes in this region already. So this is not the sun being eclipsed. This is the sun going dark, and therefore there must be an object that closely approaches the sun at this time. Now here we have a table which shows the beginning of the SDO eclipse season since 2011 until the first half of 2017. And because there are 2 eclipse seasons per year, we have 2 starting dates for each year. And the time that is shown in this column here is the time between the start of subsequent SDO eclipse seasons. So this number 183 is the number of days between March 12th and September 11th. And then this number here is the number of days between September 11th and March 6th. So that's the start of the last SDO eclipse season in 2011, and this is the start of the first SDO eclipse season in 2012. And you can see that the numbers alternate. You get a higher number of 183 and then 184. And in between you get the 178 and here 177. So that means that we have 2 periods associated with the longer orbit of this object. And one of the periods is 183 plus or minus 1 days, and the next one is 178 plus or minus 1 days. The first orbital period corresponds to the time between 2 subsequent SDO eclipse seasons in the same year, and the second corresponds to the time from the last SDO season of the year to the first of the following year. If we add the 2 periods, we get 361 days. So if we had one, so here what I did is I added 183 and 178, and that gives us 361 days. And this is the period between the first SDO eclipse season of the year and the first SDO eclipse season in the following year. And this is 4 days short of 365 days, the number of days in a year. And this is therefore the reason why the eclipse season always starts 4 days early every year, except when the year is a leap year, in which case it will start 5 days early. Now, the long orbit must therefore have a period of about 180 days, which would correspond to a semi-major axis using Kepler's third law of 0.62 AU, which is just short of Venus's orbital radius of 0.72. But Venus's orbit is close to circular. This is not. So the perihelion position for this orbit must be in the sun's inner corona, which only goes out to half a solar radius. So the perihelion position must be 1.5 r, where r is the sun's radius, because this has to be measured from the center of the sun. In other words, the object's perihelion position is 0.007 AU. That's what 1.5 r translates into in terms of astronomical units. And of course, 1 astronomical unit is the distance between the sun and the earth. So from that we can get the aphelion position, which is twice the semi-major axis minus the perihelion position. Turns out to be 1.23 AU. So the object is in an extremely eccentric orbit. The eccentricity of such an orbit is 0.99. In addition, the object's orbit takes it out beyond the Earth's orbit, which is at 1 AU. This allows the object to reach Earth and possibly interact with it. Since this is most likely a very large object, the repercussions could be dramatic, even cataclysmic. Now, once the object approaches perihelion, it changes into another orbit, which allows it to orbit the sun and reach perihelion once a day. This means that the object is in an orbit with a period of 1 day with a semi-major axis of 0.02 AU. Then the perihelion position would be the same, 0.007 AU, which means that the aphelion position turns out to be 0.033 AU. The object is also likely to follow 2 slightly longer orbits. depending on the time of the year, in order to account for the two different orbital periods observed. And here we see these orbits illustrated. So here the slightly shorter one, which I've made what I call the first long orbit, the shorter one, which would then correspond to the shorter orbital period of 177 or 178 days, and this one slightly longer, which would correspond to the other orbital period of 183 or 184 days. So each time the stellar core reaches perihelion, it remains with the Sun for 24 days, completing one rotation each day, and thus going through perihelion once per day, at which time it causes the Sun to go dark. So this is what we see. Here's the stellar core comes in towards the Sun on this first long orbit. When it reaches the perihelion position for that orbit, it changes over into the short orbit and completes 24 revolutions, about one per day, before it then exits along the second long orbit and then comes back to the Sun, repeats the process. The short orbit cannot be very specific, though, as the stellar core causes the Sun to remain dark for increasing amounts of time for about 12 days, and then the time during which the Sun remains dark decreases again until it stops after 24 days. This suggests that the object spirals in closer and closer for 12 days and then spirals out for the next 12 days, so that its orbit varies daily, shortening for the first 12 days and lengthening again for the next 12. This type of complex orbit may be the norm for other stellar cores which have invaded the solar system. The fact that the Sun goes dark at other times suggests that there are other stellar cores which have the same effect on the Sun and may follow similar orbits, i.e. a long elliptical orbit followed by a very short one, which takes the object into the Sun's corona every few hours. It is also possible that these objects follow the same orbital pattern when they arrive at the Earth, in which case they would spiral in very close to the Earth and then spiral out, thus remaining close to the Earth for several days or weeks at a time. In conclusion, the STO eclipse season's observations suggest a possible orbital pattern for stellar cores or Planet X system objects, which are observed inside the Sun's corona, and possibly also for those objects which visit and interact with the Earth from time to time. This is Dr. Claudia Albers, Planet X physicist. Thank you for watching.